This online design center helps you get familiar with the MD8710 analog front end. It requires no installation on your local machine and runs in any modern web browser, so you can set up model applications and run simulations to investigate the functions provided by the MD8710 analog front end. There are multiple ways to get started using this tool. Several templates are provided for common applications, including some simple examples to investigate output or input channels independently, as well as pulse oximetry example that will fully exercise the capabilities of the tool. A step-by-step interview can help you configure the MD8710 for your application, or you can create a new design from scratch. We'll start from scratch and recreate the impedance spectroscopy template. Here you see a functional overview of the analog front end. The wavetable defines the analog waveform that the sigma delta converter will generate. A configurable output amplifier provides filtering and gain. Both current and voltage outputs are available as stimulus signals. The blocks on the right side of the schematic can be configured to emulate sensor functions or provide circuit-based transfer functions. The analog input, including 4 configurable op-amps, are shown on the bottom of the schematic. These op-amps provide a wide range of flexibility, including instrumentation amplifier configuration, differential voltage input, or summing functions. First, let's take a look at the wavetable. The data in the wavetable has 1024 sample points, each of which has 16-bit resolution. Hence, the vertical scale ranges from -2 to the power 15 up to +2 to the power 15. The amplitude of the analog output signal will be determined by the wave scaling factor. The frequency specifies the rate at which the data will be repeated. There are multiple generators that can repeat the wavetable data at different frequencies with different amplitudes and even with different phase shifts. For example, we can take the sum of the first and third harmonics and add those together to provide them at the output of the DAC 0 channel, as shown here. A preview of the DAC 0 output is shown in the upper right corner. We could also supply the difference of the first and third harmonic signals to the DAC 1 channel, as shown here. For this example, we'll only use the DAC 0 channel with a single sinusoidal input. There should be no DC offset, so we'll generate new data for the wavetable. Here I'll choose an amplitude to range from -0.25 to +0.25 and press the Update button to update the signal. I'll now change the frequency back to 10 kHz as well, and press the Close button to save the changes. The DAC output is fed into a post filter that can be configured here. The post filter is comprised of multiple resistors, capacitors, and switches that can be changed to achieve the desired gain and bandwidth. The gain is set here. We'll choose a gain of 9 dB. A capacitor at the output of the D to A converter can be used for filtering. We'll turn the capacitor off, ending up with a bandwidth of about 1 MHz. The output can be balanced as it is here, or we can ground the positive output terminal. As shown here, the positive output is connected to the common mode voltage, or we can connect the negative output to the common mode voltage. We'll go back to the balanced mode and accept these settings. Press the Close button. Activating the transmitter block allows connection of an external circuit. This circuit can now be viewed and modified by opening the coupler block. Here we see the analog output from the MD8710 along with the pin names for these connections. There's still no circuit that we can connect to the analog output. Several circuits have been predefined that we can load into our coupler block. For this example, we'll define our own circuit. We can create a new circuit or coupler by pressing the Create Coupler tab. This brings us into a schematic editor where we can place components. A library with components and connectors is available on the left side of the schematic editor. First, we'll place the terminals that enable us to create connections to the MD8710 analog front end. Next, we'll place a capacitor by dragging it from the library onto the schematic. I can scroll down to find a resistor and place it on the schematic. Components can be selected. Using the right mouse button, the resistor can be rotated in the schematic. Double-clicking on the resistor allows us to change the component values. Components can also be copied and pasted within the schematic editor. If you're familiar with the commonly used shortcut combination Control-C, Control-V for copy and paste, those shortcuts work here as well. A wiring tool on the toolbar allows us to draw electrical connections between component nodes. I can go back into selection mode, double-click on the resistor to change the resistance value, and similarly change the capacitance value here to 470 nanofarad. And finally, it is very important that the pin types are specified correctly. An input pin means that the pin is available for connection to the outputs of the analog front end. That is, this pin is an input pin as seen from the coupler. A signal from the analog output flows from the output into the input pin of this coupler. An output pin will be available for connections to the input of the analog front end. Pin T2 will be defined as an output pin. We can now exit the schematic editor and save our work. We'll be returned to the view of the coupler. Notice that T1, which is an input node, is located on the left side, and T2, which is an output node, is on the right. We're going to assign T1 to the positive analog output. Look for the name Out0P at the end of the label in the list. You can see that the nodes are connected because they are highlighted as the cursor passes over them. I'll close this window and proceed to make the connections to the input of the analog front end. Before looking at the input connections to the AFE, it's useful to first review the basic impedance measurement. This simple schematic diagram shows the setup for the impedance spectroscopy measurement. The test signal that we already set up comes out of the post filter, flows through the load, and can be detected in the transimpedance amplifier. The virtual ground of the transimpedance amplifier effectively places the negative terminal of the impedance at ground. The output of the transimpedance amplifier is then proportional to the current flowing through the load. Two op-amps at inputs to the AFE will be configured as instrumentation amplifiers in order to detect the voltage across the unknown load. Let's now proceed with the design. I'll first activate a sensor block to assign the input signal to the AFE general purpose op-amp number 1. This will be configured for the current measurement. Now select the coupler to enter the configuration dialog. By default, a coupler circuit is provided to drive the input of the AFE. We'll remove this circuit by resetting the coupler with the predefined topology called None. This simply removes the currently defined coupler circuit. The connections and configuration of the AFE input stage are shown on the left. The Topology tab provides automated setup for the op-amp input. We'll leave the default settings. Let's make the connection to the inverting input of the op-amp. We'll assign it the terminal T2. Recall that T2 was the negative terminal of the load impedance. The other pins of the op-amp will be assigned internally in the MD8710. Close the dialog to return to the main window. We'll now open the configuration dialog for the general purpose op-amps to configure internal connections. Select the tab for general purpose op-amp 1 here. I'm going to configure this op-amp to measure current, so I have to provide negative feedback through R1. And establish the virtual ground by connecting the positive terminal to the reference voltage, VCM. This is provided by switch 6 here. Notice how switch 6 is now closed and the positive terminal is connected to VCM. Close the dialog to continue with the setup. I'll now configure the op-amps 2 and 3 as an instrumentation amplifier. I'll turn on the sensor corresponding to GPO2 and enter the dialog to edit the coupler. Again, I want to choose the predefined amplifier None. In order to connect the op-amps 2 and 3 of the AFE as an instrumentation amplifier, I can select the Topology tab on the left side of the dialog and select Instrumentation. I have to be sure to select the Input Select 1, which configures the internal switches between the op-amps 2 and 3 of the AFE. Also, we don't need the sensor, so I'll turn it off. The positive terminal of the instrumentation amplifier will be connected to the positive terminal of the test load. Again, look for the name out0p. The negative input of the instrumentation amplifier will be connected to the negative terminal of the test load, which was named T2. The external connections and switch configuration for the voltage measurement are now complete. I'll open the configuration dialog of the AFE input to define the gain of the instrumentation amplifier. Select the tab for GPO2. You can see that the switch R2 is closed, which combines the two op-amps, GPO2 and 3, in an instrumentation amplifier. The values of R1 and R2 will determine the gain of the amplifier and should be chosen based on expected values of the test impedance. I'll set R1 to 12.5 kiloohms and R2 to 25 kiloohms. The feedback capacitance can be adjusted to modify bandwidth. Select the op-amp GPO3 to set those resistor values as well. GPO2 and 3 are now configured to measure the voltage across our test load. Close this dialog to save the changes. I've put quite a bit of work into setting this project up, so I want to be sure that the project is saved and that I can open it for later use. I can save it here and add a descriptive comment, and even share it with colleagues for later use. The setup is nearly done. Op-amp outputs are fed into preamplifiers that feed the A to D converter. Select here to open up the configuration of the preamplifiers for the A to D converter. I'll set the gain of the preamplifier to about -18 dB. The output of the general purpose op-amp 1 will be applied to the inverting input. The common mode voltage will be assigned to the non-inverting input. The preamplifier 1 combines the signals from the op-amps 2 and 3 to complete the instrumentation amplifier for voltage measurement. I'll set the gain to about -13 dB. The switches for the op-amps 2 and 3 should be correct because I previously selected the instrumentation amplifier configuration. The op-amp 2 output is connected to the non-inverting input, while the op-amp 3 output is connected to the inverting input. The analog front end is now configured properly and ready to simulate for impedance spectroscopy measurements. Select the Simulation tab at the bottom of the window to proceed with the simulation. The Transient Simulation includes the details of the D to A and A to D conversion, so the simulation takes a little while. The default 500 microsecond simulation time is suitable for this example. I'll start the Transient Simulation now. The status of the simulation will be shown in the information window. This simulation will take about 13 minutes. The estimated simulation time shown here is a very rough estimate. When the calculations are done, the message window will indicate that the post-processing data is being generated, as you can see here. When the simulation is complete, the results will be displayed as shown here. Clicking on any of the graphs allows us to take a closer look at the signal data. This post-processing capability provides zoom-in functions. We can reset the zoom. Notice that the total current timescale or inverse timescale can also be displayed. Let's close this window and take a look at the other data. Notice that the output from the GPO1 looks like it's going into saturation. It looks like the gain of the transimpedance amplifier realized with GPO1 was too high. This caused the output of the op-amp GPO1 to go into saturation. I'm glad I caught this mistake early in my design process. I'll now select the data that I'd like to see in my summary. I'll select the transmit signal, the output from the post amplifier, as well as the output from the preamplifiers. I can proceed to view a summary of my project, which shows configuration and connectivity of the various stages, as well as the simulation data selected on the previous page. I can download this summary as a PDF file, and I can also download the configuration file so that I can realize the same configuration in my hardware that I used for this simulation. This concludes the demonstration of the Online Design Center for the MD8710 analog front end. If you have feedback or comments, please be sure to provide these using the link in the upper right corner of the page.